Welcome to the 8th presentation in the 5th webinar series presented by the International Adsorption Society. The IAS is an international organization dedicated to advancing adsorption as a solution to scientific, engineering, and human welfare challenges through the promotion of adsorption research and education. We thank everyone for attending the webinar today. The webinar series has been an immense success, and the recordings of previous webinars continue to be viewed on YouTube and Bilibili. This is the 8th webinar of our 5th series, which we will continue to have monthly throughout the year. We intend to continue with a variety of speakers from industry, academia, and other research institutes, as well as PhD students and early career researchers. Announcements regarding the 5th series will be distributed through the IAS mailing list and the IAS Twitter feed. Today's webinar will be given by Dr. Alireza Hejazi at the Amirkabir University of Technology in Iran. I am Nicholas Wilkins at Svante Technologies Incorporated in Canada. Today's webinar will be moderated by Giuseppe Pezzella at King Abdullah University of Science and Technology in Saudi Arabia. We are required to remind attendees and future viewers that the views expressed by the speaker, host, or other moderators are not necessarily those of the IAS or the institutions associated with those individuals. We ask that you consider joining the IAS as a regular member if you have not already. Our dues are minimal, only $20 per year, but to support the publication of our flagship journal, Adsorption, contribute to travel grants, and workshop seed funding for IAS members and affiliated groups, as well as aid the organization of our triennial conference on the fundamentals of adsorption. Members also receive free access to IAS-supported materials, including our journal, as well as the adsorption database published by Springer Materials. Anyone can follow the IAS on Twitter at @intadsots for future updates regarding IAS events, webinars, and information about scientific meetings. We have also started a LinkedIn group, which can be found by searching the International Adsorption Society. Please help us expand our YouTube channel by liking this video and subscribing. I'll now hand it over to Giuseppe, who will moderate the YouTube Q&A.
Thank you, Nick, for your introduction. It's my pleasure today to welcome Dr. Alireza Hejazi to today's webinar session. Dr. Alireza Hejazi is an assistant professor at the Department of Chemical Engineering at Amirkabir University of Technology and heads the AUT Office of Sustainability. Prior to joining AUT, he was a postdoctoral research associate at the Department of Chemical Engineering, Imperial College, from 2017 to 2019. He holds a PhD and Master in Chemical Engineering from the Department of Chemical and Materials Engineering at the University of Alberta in Canada. His research interests center on adsorption separation processes, with the particular focus on high-purity oxygen production, helium separation, carbon capture and storage, and optimization of adsorption processes. During the webinar, questions can be submitted to the speaker as comments on the YouTube live stream. Questions will be answered at the end of the presentation. With that, I welcome Dr. Alireza Hejazi again and pass over the presentation to them. Thank you.
So Ali, we're not able to hear you.
Yes, so can you hear me now?
Yes, now we can.
Wonderful.
Okay, I'll spotlight your video.
Yeah, okay. So hopefully everything is okay now. Hi, everyone. And thank you very much, Nick and Giuseppe, for the introduction. And thanks to the International Adsorption Society for providing this opportunity. My name is Alireza Hejazi from the Department of Chemical Engineering at Amirkabir University of Technology here in Iran. And today I'll be presenting on the topic of enhancing medical oxygen concentrators, the focus on basics, and then on offering a cost-effective care using flexible absorption processes, machine learning, and patient-centric design. Now, before we delve into the technical aspects, I'd like to acknowledge two groups of people. On the left, those who shaped my journey, and I've learned a lot from them in the field of absorption, specifically my PhD supervisor, Arvind Rajendran from the University of Alberta, and my postdoc mentor from Imperial College London, Dr. Ronnie Pini. I'm not sure if they're here today, but thank you both. And on the right-hand side, I'd like to express my gratitude to the talented master students who have significantly contributed to the work that I'm presenting here. And they have all graduated from my group. Kimia is now a PhD student at the University of Manchester. Muin is soon to embark on his PhD journey ahead. And Fatima is now currently a process engineer at a local EPC company here in Tehran. With that said, let's move on to our main topic. Oxygen therapy is a lifesaver for many people with respiratory conditions like COPD, and sadly, it's the third leading cause of death globally. Now, medical oxygen concentrators, on the other hand, have become increasingly important thanks to the technological advancements and the rise of home healthcare recently, and the recent COVID-19 pandemic, which exposed the flaws in the traditional supply chain of high-purity oxygen. Now, MOCs, they use pressure or vacuum swing adsorption technology to extract oxygen from the air, providing a reliable oxygen source for the patients. As you can see from this graph, the demand for MOC is set to consistently increase in the coming years, but there are still challenges like the high cost, the maintenance requirements, and the complex regulations that are in place. Now, speaking of challenges, the COVID-19 pandemic really highlighted the fragility of the global oxygen supply chain. Suddenly, the demand skyrocketed, leading to widespread shortages, especially in developing countries. And to make matter worse, many high-performance medical oxygen concentrators rely on lithium-based components, whether that being the adsorbent itself, like Lithium X, or the batteries. Now, with limited resources and the growing demand, as you can see in this figure over the next decade, you see that the demand for lithium is set to almost explode in the coming decade, and we all know why. This would result in the rise of the prices of lithium-based components in the MOCs, eventually the rise in the price of MOCs themselves, and of course, the availability of common adsorbents like Lithium X, which is the gold standard for medical oxygen concentrators. And on top of that, the current technology is not very energy efficient, and this would lead to higher operating costs. Now, all of these emphasize that there is an urgent need to reduce our reliance on scarce resources like lithium-based adsorbents and develop energy-efficient, smart, flexible, cost-effective systems. And this is what we're going to talk about today. We're going to discuss how we can improve it and what we can do to do better. Now, let's talk about different types of MOCs that are available on the market now. There are mainly two types of MOCs. One is the stationary oxygen concentrator, known as SOC, and the other type is portable oxygen concentrators, known as POCs. SOCs are great for home use. They are, especially when high oxygen flow rates are needed, they are reliable, offer consistent performance. However, they are not really very portable. So they are best suited for, as the name says, stationary use. And on the other hand, portable oxygen concentrators, the POCs, are designed for mobility and flexibility. So they are perfect for people who need oxygen on the go, but they have their own limitations, such as the low oxygen flow rates and shorter battery life compared to the SOCs. Now, given the SOCs' larger size and more complex design, they offer more opportunities for improvement compared to tiny POCs, and therefore, for the rest of this presentation, we'll focus on these stationary oxygen concentrators. Okay, now, we are going to use adsorption-based separation for this application to concentrate oxygen. And we all know that it's a process that involves using materials that selectively grab to the nitrogen, leaving behind the oxygen-enriched air. The efficiency of this process depends on the right combination of the adsorbent and the process design. And choosing the right material and process is crucial. So we usually look for materials that have high selectivity, good equilibrium loading, good equilibrium capacity, good working capacity. And from that perspective, but from a process perspective, we also consider factors like higher purity, high recovery, low energy efficiency, high productivity. The key is to match the material properties to the optimal adsorption cycle. So how do we achieve this? It's all about detailed process modeling and optimization, and that's the only way that you can achieve this, to basically, as we have shown in our collaborative work with Dr. Rajagopalan from the University of Manchester, each material needs to be married to a process to maximize its potential for any gas separation. And this application is nothing different than the other adsorption processes. So what is our solution? What is our solution? So imagine a patient at home or in a hospital, and if it's during the demand of high demand for oxygen, at home or hospital, relying on oxygen therapy. What kind of device do they need based on what we discussed so far? To address the challenges we talked about, they would need a device that is a smart, adaptable to different patient needs, and of course, cost-effective. And to achieve this, we need to explore alternative adsorbents rather than the gold standards like lithium LSX. We need to improve energy efficiency, and ultimately, we need to develop patient-centric solutions, patient-centric devices that can adapt to various conditions and needs. And these devices, ideally, we want them to be remotely adjusted by the healthcare providers. So this is the idea behind all the work that we're doing. And today, I'll be presenting parts of that to show you the importance, things that we have done, and how we can move towards designing a smart, efficient, flexible medical oxygen concentrator. Okay. To achieve this, we have selected 6 nitrogen selective adsorbents to test. Lithium LSX, again, the gold standard for oxygen purification. Zeolite 13X, Calcium X, Silver ETS10, and several lithium LSX. So the last two, the 2 silver exchange materials, they can differentiate between argon and oxygen, so they are argon selective. And this allows us to achieve oxygen purities over 95%. The figure on the right shows nitrogen adsorption equilibrium, and the one on the right is for oxygen for all the 6 materials at 298 Kelvin. if you look at this figure, the first thing that you will observe is that calcium X and lithium X, they exhibit the highest adsorption capacity. And interestingly, every material, each material, has a unique adsorption behavior. Some of them are linear, some of them are slightly nonlinear, some of them are argon selective. We're not showing argon isotopes here, but the silver exchange ones are argon selective. And by looking at the isotome itself, you will have a clue which material, which process to use for every material. You'll have some ideas. But to answer this completely, what you would need to do is to do a detailed process modeling, process optimization. So to define the adsorption isotopes, we've used a dual-side Langmuir model to fit the experimental data and integrated the results into our detailed mathematical modeling, which I'll explain in the next slide. Okay. So to predict how these adsorbents would perform, we use a comprehensive modeling approach. This involves solving a series of partial differential equations simultaneously that account for all the physics, for adsorption dynamics, for energy balance, for the pressure drop. And we have used finite volume technique to discretize these equations in a space and integrate them over time using MATLAB. So I won't go into the details of the modeling because it has been extensively discussed in the previous works from our group, from other groups, and you can refer to those if you're interested. I refer you to those works to learn more about the modeling approach. So we know which materials we have used. We know how the model works. Let's discuss about the cycle configuration. There are two common cycles used in the NOCs, the Skåström cycle and the 6-step cycle wet pressure equalization. Both can be implemented using PSA, VSA, or PVSA. And the Skåström cycle involves steps like adsorption, where we obtain the raffinate product, here being the oxygen, blowdown or evacuation, where we regenerate the column at low pressure, light reflux, where we reflux part of the product, part of the light product back to the column, and pressurization with the feed, where we increase the column pressure back to the adsorption pressure. The 6-step cycle, on the other hand, has an extra pressure equalization step where we equalize the pressure between two columns, and this would help us save a bit of energy. Now, both cycles have many operating variables that can be optimized based on the specific adsorbents that is being used, and these parameters are times of the steps, the low pressure, the high pressure, and the velocity of the feed. Usually this is what we use if the system size is fixed. Now, each of these configurations have their own pros and cons, but for the rest of this presentation, we'll only focus on this Skåström cycle and evaluate the performance of our materials through process optimization. Excuse me. Now, our optimization framework uses a genetic algorithm to fine-tune the operating parameters that we discussed about. And we can even extend this to a more holistic, unified approach where the optimizer can also decide about the best cycle, being that an integer variable, or the best material. Now, the optimizer is going to provide these inputs to the detailed model, here our mathematical model, which simulates the process and predicts key performance indicators like oxygen purity, oxygen recovery, flow rate, energy consumption, cost, and things like that. And then the optimizer penalizes the KPIs that don't meet our target and calculates the objective functions, which could be a multi-objective optimization problem, like purity and recovery at the same time, or a single objective mixed integer nonlinear programming that have been shown in our recent work. You can refer to that if you're interested. Now, if you keep this iterative process over and over until you reach the optimal solution, the results, and we are going to see this a lot in this presentation, the results are often visualized as Pareto fronts, showing the trade-off between two different performance indicators. The points below the Pareto front are the ones which are suboptimal, and the area above is the infeasible region. The Pareto itself is the optimal solution. Now, instead of the simulator here, one may use a surrogate model that can significantly increase the speed of optimization. So instead of a detailed mathematical model, if you have a machine learning-based surrogate model, you can quickly predict the performance indicators and as a result, quickly do the optimization. And this is what we have done in this study. To streamline the optimization process, we developed machine learning surrogate models using the structure defined in Dr. Rajan's run group over the past few years. We generated a massive data set of 35,000 input and output combinations using our detailed model. And then we considered 17 input variables categorized into 4 different groups. And after pre-processing the data, we trained a neural network with 3 layers and 24 neurons per layer. We used 90% of the data for training and 10% for testing. And I'm going to show you how we conduct the assessment and towards the end of the presentation. Now, this machine learning model can quickly predict, as I said, the performance of different adsorbents based on factors like the operating conditions, adsorbent properties, Longmuir model parameters, bed characteristics, and cycle parameters. So we have 17 input variables introduced to this machine learning model, and then we get the prediction of the performance indicators quite quickly and efficiently. Now, ultimately, the proof is in the pudding. So to validate our simulations and optimization results, we have also designed and built a fully automated bench scale PBSA, right, in our lab, where we get input from the real experiments. We basically modify and improve our model. And this experimental setup is crucial to ensure that our models can accurately capture real-world conditions. And of course, for identifying any practical limitations that we're going to have during the experiment or in the mathematical model. So this was about the methodology that we're using in different parts of this work. Now, let's take a look at some of our results. So here I have plotted the purity recovery and purity flow rate Pareto fronts for the PSA process, with each adsorbent represented by a different color. The first thing that you can read from this figure is that in PSA process configuration, 13X and Lithium X, in both optimizations, they are the top performance, achieving high flow rate and high recovery, while maintaining excellence in their purity. And interestingly, while Lithium X and 13X, the black and the green points, they perform almost identical in the purity recovery fronts. That's not the case in the purity flow rate. And this is probably likely due to the higher adsorption capacity for nitrogen and lithium LSX, which allows the optimizer to select larger feed velocities, as shown in this box here. So here I'm showing the chosen feed velocities for the Pareto fronts, for the Pareto points, for Lithium X in black and 13X in green. And we see that the optimizer has chosen higher values of feed velocity for Lithium X resulting in higher flow rates eventually. In terms of energy, both materials behave the same. So if you look at medium rate flow rates, we're talking about something around 3 to almost 10 SLPM. They behave almost similar. What we can get from these results is that these observations, they emphasize the importance of evaluating adsorbents from multiple perspectives, not only relying on purity recovery, which is a very common practice in some of the works that are being published from various researchers. Not only relying on purity recovery, not only relying on energy flow rate, we have to rely on all the KPIs, compare the materials, and then decide which material is the one that we use, which one is the alternative. Now, speaking of the VSA process, so these were all about the PSA. Speaking of the VSA process, again, I showed the same thing, purity recovery Pareto front, purity flow rate Pareto fronts. What we can see is that for the VSA process, lithium LSX in black, calcium X in brown, and silver lithium LSX in blue were the top performance, with lithium X delivering an impressive 15 SLPM of medical grade oxygen with plus 80% purity. Another thing to highlight is that both silver exchange adsorbents perform better in VSA compared to PSA, and this is likely due to the slight nonlinearity that we have seen in their isotopes. Now, another key observation here is that it seems that flow rate is the key decision-making in the VSA process. So if you compare these materials together, you see that they are more or less within the same value of energy consumption, but they have completely different flow rate ranges. And it looks like in VSA process, basically the flow rate is the key decision-making criteria, whereas in PSA, it was the energy consumption, not the flow rate. And our results suggest, at the end of the day, that calcium X is a viable and cost-effective alternative for VSA, for lithium LSX. As we discussed initially, it's a lithium-based adsorbent, and there are challenges. So calcium X seems to be a viable and cost-effective alternative, and it offers a good balance between the performance and the cost. So far, we basically looked at one-to-one optimizations. That means pairing individual materials with specific processes, so one-to-one optimizations. We've also taken as another step ahead, and we've taken a more holistic approach by incorporating all the adsorbents, all the 6 choices, 5 or 6 choices that we have, and all the process configurations, so PSA and VSA. So 5 materials, 2 process configurations, and this would mean 10 material process combinations. Now, instead of running 10 separate optimizations, using the approach that we've developed, the unified material process optimization, we can now run a single optimization that would give us a lot of time saving, at least for 30%. And interestingly, the result confirmed the success of this unified approach, which can be highly beneficial for large scale optimizations. For example, here we study all the materials, we study PSA and VSA, and you see that in this region for the purity above 95%, silver ETS10 is the optimizer suggests silver ETS10, then it's silver lithium LSX, and then it is the lithium LSX adsorbent. So moving away from that, we identified lithium LSX. We all knew that lithium LSX is the gold standard. We all identified lithium LSX as the top performer, and we explored its full potential. So here we're going to use PVSA. See, what is the full potential of lithium LSX? We saw in PSA, we saw in VSA. Now we want to see how it performs in the PVSA process. PVSA consistently outperformed both PFA and VSA. You can see PVSA, the hollow triangles here, it's always outperforming PSA and VSA, the solid symbols, and it offers significant energy saving as well and higher recovery rates compared to PSA and VSA. And to highlight a few facts about that, if you look at these 2 points here, these 2 points, they both have flow rates of around 10 SLPM, but we saw up to about 30% reduction in the energy consumption compared to VSA when we use PVSA. And if you compare PVSA and PSA, these 2 points here, you see that PVSA almost doubled the flow from 7 to something around 13, while nearly halving the energy requirements compared to the PSA. And although it does require both a compressor and a vacuum pump, which is its limitation, but it performs much better. Okay. So far, all the key performance indicators that we discuss about were the traditional ones that we basically look into. All of us consider purity, recovery, when you want to judge which process is better, which material is better. We have taken a step forward. We have moved towards a more patient-centered approach. We integrated patient needs directly into the optimization process, and this was very, very important part of this work. So we discussed with the doctors, with medical doctors, and we decided to include fraction of inspired oxygen, known as FiO2, as a key performance indicator in our optimization routine. FiO2 basically measures the amount of oxygen in each breath. And as it can be seen from the formula here, it is calculated based on the oxygen flow rate from the MOC plus what is being inhaled from the atmospheric ambient airflow. And these two will be mixed later before the delivery to the patient, so they provide the oxygen that the patient requires. Now, by incorporating FiO2 into our optimization routine, we can ensure that our solution can meet a wide range of patient needs, from low to high oxygen flow rates. So we have done this optimization, and here we see FiO2 product flow rate up front for different materials. Interestingly, we see that there is a turning point for the flow of FiO2 fronts, and this comes from the definition of the FiO2, the trade-off that you have between purity and flow rate, as we have seen previously. Now, if this turning point is more towards the right-hand side of the figure here for PSA, that means the material or the adsorbent, the combination of material process, can cover a wider range of oxygen treatment, here for PSA, in the middle for VSA, and on the right-hand side for PVSA. Now, for example, if we look at these 2 points here, we see they both offer an FiO2 of 0.5, but at two completely different purity flow combinations: 30, 50% purity, 8.5 SLPM, 93% purity. And this shows the importance of considering both FiO2 and flow rate when optimizing the design. Additionally, these results further confirm basically the suitability of 13X and Calcium X. If you look at here, Calcium X in VSA is the next after lithium LSX, and 13X in PSA is the second ranked adsorbent. Now, patients undergoing oxygen therapy can be divided medically into 3 different groups based on the FiO2 and flow rate ranges that they require, as well as the type of oxygen delivery device that they use, being nasal cannula, simple face mask, or the non-rebreather mask. And if we look at our optimization result, we can clearly show the limitations of each process material combination. For example, lithium LSX using PVSA, this front towards the right-hand side of the figure, it can fully satisfy the needs of the first and the second group of patients, but it can partially meet the needs of the third group of patients, which are under severe oxygen therapy. They require about 0.6 to 0.9 FiO2. Now, this would help us to visualize these results using a graphical guide, and this is where we spend a lot of time to prepare these graphical guides, where the red color basically indicates an inability to meet the requirements. For example, Zoelite 5A using PSA cannot satisfy the needs of patient group number 3. Green indicates full satisfaction, and yellow indicates partial satisfaction. And we hope that this graphical guideline allows rapid assessment of adsorbent performance under different conditions, which would make it easier to choose the suitable material during critical shortages like the COVID-19 pandemic. So at that time, we didn't know what to do. We didn't have lithium LSX. There were other adsorbents available, and we didn't know if we should use it for PSA or VSA, or if it's going to satisfy patient group 1, patient group 2. So this graphical guideline would facilitate that. Now, taking another step forward, if we combine all the operating data points that we have for lithium LSX and VSA, we get a plot like this. So this is a rather complicated plot. I'm going to briefly introduce that. So each point on this plot, again, product flow rate against FiO2, each point on this plot represents a specific set of operating conditions with the color indicating energy consumption. Blue for low energy consumption, red for high energy consumption. And interestingly, an interesting observation is that for a given FiO2 of, for example, here, 0.4, any point on this line can meet the patient needs. However, there is a specific energy optimal point that offers the lowest energy consumption, around 60 to 70% save in the energy. Now, speaking of flexibility, and this is a very important part of this work again, speaking of flexibility, during the periods of high demand, again, like the past COVID pandemic, multiple patients are often connected to a single MOC, and this can limit the maximum achievable FiO2 and shift the optimal operating points. For instance, connecting 2 patients to one MOC can reduce the maximum achievable FiO2 to 0.42 from a value of around 0.55, and it will also change the best operating points in terms of energy efficiency. So for example, here, if you choose this point, you are going to save around 40% energy compared to the case that you were using this point, meaning 2 separate MOCs for 2 separate patients. If you combine them, if you can satisfy their need medically, then you can save around 40% in the energy. And this flexibility is crucial during the shortages, allowing a single concentrator to serve multiple patients and conserve resources. So we have a gold standard that we can use under situations like that. Now, while our detailed model provided accurate results, it can be computationally demanding, especially for larger scale optimization problems. To address this, we have developed a machine learning-based surrogate model, and this was developed by Moeen, that can significantly speed up the optimization process. So here we see the parity plots for 500 unseen data points that is confirming the accuracy of our machine learning model for the 4 common KPIs that we use. And we have also further assessed the model generalizability, where we compare the Pareto fronts obtained from both the surrogate model and the detailed model. So here, the lines represent the Pareto front for purity recovery for 3 different process configurations: PSA in red, VSA in green, PVSA in blue. For zeolite lithium LSX, the lines are the machine learning-based model optimization. The points are the detailed mathematical model-based optimization. The close agreement between the two highlights the model effectiveness. And this would eventually basically have the potential to revolutionize the MOC design. For example, by enabling the development of intelligent devices that can adapt to changing operational conditions and eventually leading to smart oxygen delivery and improved patient care. And this is the goal, the final goal that we are looking for. So in addition to this model, the machine learning-based model, basically gives you the freedom to evaluate the performance of any material, and I emphasize, any material in a column of any size. And this basically motivated us to evaluate the performance of mixed adsorbent beds composed of lithium LSX and 13X. And this is what I'm going to do in my next few slides. Why did we do that? Why did we think about mixed beds? So this concept is very similar to the recent work out of Dr. Ronnie Pini's group on mixed adsorbent systems for carbon capture. And our approach involves using a weighted average of lithium LSX and 13X in a well-mixed column, and then compare the results with the pure cases. We're basically constructing a weighted average isotherm, depending on the weight fraction of, for example, zeolite 13X that you have in the column, and then we optimize the mixed adsorbent system using our flexible material machine learning model quickly in a matter of minutes. Now, given that lithium LSX offers higher flow rates, we have already seen it, offers higher flow rates, offers lower energy consumption compared to 13X, but 13X is cheaper on the market. The price ratio at the moment is around 30. So lithium LSX is 30 times more expensive than 13X. So we want to explore the potential of combining them in a mixed adsorbent bed to see how does this interplay of operating cost, energy, plays against CapEx, the price of the adsorbent itself. And this approach will allow us to balance the operational and capital costs while meeting the patient needs. Now, to optimize this mixed adsorbent system, we conducted a series of cost FiO2 optimization. So we see the cost made up from OPEX, adsorbent cost, and the power cost. And we also incorporated 2 additional key variables in our study: the electricity price, dollars per kilowatt hour, and the price ratio of lithium LSX to 13X, because it is going to fluctuate a lot. The latter, the price ratio, has fluctuated significantly over the past 2 to 3 years due to the recent lithium shortages around the globe. Now, so here I present the cost against FiO2 front for various mixed bed adsorbents with different weight fractions of 13X. The figure on the right, on the left, shows the result for an electricity price of 15 cents per kilowatt hour, while the figure on the right is for 45 cents per kilowatt hour. The price ratio is fixed in these figures around 30. And each bed design is represented by color, with lithium LSX shown in pink and 13X shown in blue. These shaded regions, the shaded regions indicate the cost-effective FiO2 level that basically justifies the use of that bed design, that mixed bed design. For example, here we see that that lithium X is the preferred, is the one that has the lower cost, lower overall cost, but here 13X has the lower overall cost for this range of FiO2. As shown, lithium LSX, in both cases, lithium LSX has better performance at higher FiO2 level, justifying its higher initial investment, whereas 13X cost-effective range of FiO2 shrinks from something around 0.3 to 0.5 FiO2 to around 0.3 to 0.4, 0.42 FiO2 when you increase the electricity price from 0.15 to 0.45. And this is due to the higher energy consumption of 13X compared to lithium LSX. So this basically tells us the interplay between the capital and the operating cost is very important. And it is very important in selecting the optimal absorbent configuration for the MOC design, depending on electricity price, depending on the price ratio of different materials. One can extend this work to many other adsorbents, many other mixtures, and see how it will show up. Now, with that said, I would like to summarize our key findings. We all saw that lithium LSX was the top performer. 13X was the second choice in the PSA configuration, and calcium X was the second choice of the lithium LSX in the VSA process. We have successfully integrated medical indicators, key performance indicators, such as FiO2. This is what the patients need. This is what the doctors need. We have integrated medical requirements into our optimization framework, hoping that we can bridge the gap between the doctors, the medical community, and the adsorption community, the chemical engineers. And we have also shown that our machine learning model, combined with economic assessment, can basically lay the groundwork for the development of a smart, adaptable, and cost-effective devices, which is the final goal of this study. And with that, I'd like to conclude by acknowledging the past and the present members of my group, the Laboratory of Adsorption and Separation Processes here at Amirkabir University of Technology, where all this research was conducted, and these are the people who are doing most of the work. And thank you very much for the invitation again. Thank you very much for your attention, and I look forward to your questions. Thank you.
Thank you, Dr. Hejazi, for your great presentation. We are having some questions from our YouTube channel. The first one is Yavad Imanipur. He is asking if are there any cost-effective materials that are used in this category?
So the figure that I'm showing here basically shows the cost effectiveness used in the PVSA process. And here you can see, for example, different weight fractions of lithium LSX and 13X, depending on the electricity price, depending on the cost ratio. They are either of them or either of these weighted fractions are basically applicable for a certain range of FiO2. For example, if you aim at systems that are going to be mostly used within the range of 0.4 to 0.5. And if the electricity price in your country is around $15 cents per kilowatt hour, and if we stay at the price ratio of 30, which we are now, then 13x is the optimal choice. But if we're aiming at satisfying the need of patients, which are in patient group 3, the high flow rate, high FiO2 range, then your only choice would be lithium LS6.
Thank you. I'm sure this will answer the question. I have a follow-up question on that.
Sure, Giuseppe.
Do you have any idea about the prices of these devices? And as my understanding that this comes from an emergency situation, but market-wise, what's their main advantage compared to nowadays used devices?
So the main advantage there, this is a very wonderful question. So for the price range, we're looking into $2,000, $1,500 to around $2,000 to $2,500. The main advantage there is moving towards designing the smart devices. For example, and it's not just about the COVID situation. For example, you have in many countries, you have many patients which cannot easily travel to cities. They're living in islands far away from the main hospital. You cannot easily access them. If you have a device that is smart, if you have a device that is flexible, it will satisfy their need. The doctors, the medical staff, they can control it from distance, but it is smart itself based on the work that we have done. Using the machine learning based model, it can quite quickly adapt itself to the patient's need. When the doctor prescribes oxygen therapy, they usually give FiO2, flow rate, and the duration of that treatment. So if the system is smart enough to adapt itself, so it saves a lot of energy, first, and second, satisfy the needs of the patient, this is the key component of this work. Apart from that, you're right. Satisfying the needs of patients during the time of high demand and emergency conditions like the COVID pandemic is the second goal of this choice.
Everything is clear. Thank you so much. We have another question from our YouTube audience. It comes from Amir Elahi. He's thanking you for the presentation, and we'd like to know, how are you simulating the mixed bed conditions? Are you only changing the isotherm? Does the configuration of the adsorbent in the bed have any impact?
Yeah. So this is, again, a very good question. So the way that we have looked into the mixture, we have rebuilt the isotherms using weighted average of the loadings of the two materials. And this is also extensively done in the work from Ronnie Pini's group. We have assumed the physical properties like the CP, again, to be the weighted average of the two materials. This is a simplified assumption, but since 13X and lithium LS6, they have a very similar structure. So they're from the same family of materials. I think we can assume assumptions like that. And then from there, the weighted average physical properties and thermodynamic properties. Then we introduce the isotherm parameters into our flexible material machine learning model, and it will give us the cost FiO2 optimization per front as we see here.
Excellent, excellent. Since we are here, I have a personal question regarding the mixed bed. Do you have any guard bed before you are actually separating, due to the fact that zeolite 13X performances might be affected by water?
Yeah. So in all our optimizations, we assumed a dry feed, and this is what is actually happening in reality. You usually have a protective layer of activated alumina or silica gel to protect the molecular sieve from the humidity that you have in the air, in the ambient air. But in our simulations, we have considered dry air as the feed.
Thank you. We have another question from our YouTube channel. It comes from Bob Grasso. He thanks, of course, you for the nice talk. And he say, can you tell me what is limiting the flow rate for 13x beds? If it is the pressure drop, what would you expect the results to be if the pressure drop is reduced by 50%?
Yeah. So the limitation, I think the audience is he or she is asking about what we see here. Let's move on to here. So for example, sorry. Okay. So it had a bit of a delay, so I need to go back to that slide. Sorry. Yep. Here. So he's asking about this. Why is 13x lagging behind? And this is coming from the isotherm. This is coming from the thermodynamics. If you look at the isotherm for 13x as compared to lithium LSX shown here, you see that 13x has a much lower nitrogen capacity, and this would result in lower flow rates compared to lithium LSX. Pressure drop in these systems are not huge, although one needs to take care of that because you usually use tiny particles, around 500 micron particles, to increase the productivity of the system. But usually we don't have any trouble with regards to the pressure drop in medical oxygen concentrators.
Thank you. Thank you so much. I have another question.
Of course.
While there is no really hard specification on recovery, is there any desired value that makes a material or process combination favorable compared to another one?
Sorry, can you repeat your question, Giuseppe? I didn't quite get that.
Yeah. Looks like there is no hard specification on the recovery, like for example for CO2 capture. And so I'm wondering if based on that, there is any desired value that makes the process or the material more favorable than another one.
So the reason that you do not have any constraints on the recovery like CO2 capture is because your feed is basically free. It's the ambient air. So you don't really care a lot about losing what you're introducing, but it is important when you're looking into delivering high flow rates to the patients, as we saw here. I'm not sure if I answered your question, Giuseppe.
You definitely did.
Okay.
Thank you so much. I think we can say we are almost done with the question, and I can hand over the mic to Nick.
Okay. Ali, you can turn off your video for the moment. Okay. Oh. All right. Thank you, Dr. Alireza Hejazi, for your presentation, Enhancing Medical Oxygen Concentrators, Delivering Cost-Effective, Patient-Centered Care Through Smart, Flexible Solutions. We also thank all of our attendees for joining this webinar and hope that it was both educational and enjoyable. An edited version of this webinar will be posted on the IAS YouTube channel in Bilibili with an announcement on the IAS Twitter feed. The hope is that the work discussed here today will be a useful resource for the adsorption science community in the future. We'll be taking a break in December and will return in the new year. The next confirmed IAS webinar will be given by Dr. Yu Wang on January 22nd at 1400 UTC. Announcements regarding the next webinar and other IAS online events will be posted on our Twitter feed and through the IAS mailing lists. With that, we thank you for joining us and hope that you will join us again soon.